2.2, derivative as a function. In these sections, we're going to look at the derivative of a functions in general. Okay? Previous sessions, we defined a derivative of a functions at a fixed number. Right? Derivative of a functions at a fixed number a. So which is f prime of a, denoted f prime of a, equal to limit as h approaches 0, f of a plus h minus f of a over h. Now we want to look at, instead of one particular point, we want to look at what everywhere. So the only thing that's going to change is what, instead of a specific number a, we will be having what, variable. So therefore, this second formula will not be used as widely anymore, because we don't want to write down f of x minus f of x over x minus x. Okay? So the derivative of a functions at any points x, we will denote it at f prime of x, that is equal to limit as h approaches to 0 of f of x plus h minus f of x over h. And the limit must what? Exist. Okay. Then the notations that we can use is not only f prime. Okay. If we have an equations later on, we're going to talk about implicit differentiations. Then if we say that y as a functions of x, right? Y equal to f of x, then we can denote the derivatives of the function as y prime, or dy over dx, or df over dx, which is f is like the name of the functions, or d dx f of x. So it's basically referring to derivative respect to x, where you can see that x is independent variable and then y is a dependent variable. Right? And we can also denote it d f of x and dx f of x. Once you go into Cal 3, right, multivariable calculus, you're going to be taking derivatives of not only one variable functions, it will be a multivariable functions. So for example, right now we are looking at f of x. Later on, you can have f of x, y, right? Those multivariable functions. So this notation's derivative, the uppercase D, is used to in multivariable functions more often, because we can talk about derivative respect to x first and then y of a functions, or derivative respect to y first then x directions of respect to the functions. So this is for later purpose. Okay. Then now we know that derivatives, right, is the operations, right, differentiations operations. So d dx derivative respect to x, and differentiation, operations of differentiation is basically a process of calculating what? Derivatives. So later on we would use this differentiable, okay, terminology. For example, in definitions, next definitions, the function is differentiable at a if f prime of a exists. So we can say that f is differentiable at a when f prime of a has what? A value to it. That means the limits exist, right? This limit exists. And it is differentiable on an open interval a to b, a to infinity, negative infinity to a, or negative infinity to positive infinity if it is differentiable everywhere, right? Everywhere of the function. So the very first example that we're going to do is taking derivative as a functions, right? And we want to use the definitions. So you notice I use the definitions to find the derivative of the given functions. So when we compute on this, that will be f prime of x. That is basically what limit as h approaches to 0 of f of x plus h minus f of x all over h. So we want to now simplify this limit as h approaches to 0, substituting the functions with x plus h. So that's basically x plus h in the numerator, and in the denominator x plus h, minus the function, which is going to be x over x minus 9. My bad, this should be 9 minus right there, and all over h. So now, to simplify this further, I need to multiply the numerator and denominator by LCD, which in this case, the LCD is x plus h minus 9 and then x minus 9. We're going to multiply both numerator and denominator by that to clear the fractions. So when I do that, that will become, on the numerator, it will be x plus h times with x minus 9 minus the second term, x minus 9 cancels out, so it will be x times x plus h minus 9 all over h times with x plus h minus 9 times x minus 9. So continue simplifying this. That will be limit as h approaches to 0 of, you're going to FOIL it, distribute it, right? And then the denominator, I'm going to leave it like it. So after I FOILed it and then reducing like term like x squared is gone, x plus h and then x minus h is gone, 9 x and then minus negative 9x is gone. So therefore it's only left with negative 9h. Right? And all over h, x plus h minus 9, x minus 9. So now, finally, if I reduce h on both of them, both numerator and denominator, that will give me negative 9 over x plus h minus 9 and then x minus 9. Now direct substitution is applicable, so when I substitute 0 for h, so that will become x plus 0 minus 9 and then x minus 9. So therefore, I got negative 9 over x minus 9 quantity square. And this is my derivative of the functions, which is f prime of x. Let's take a look at on the next example. And this time we will be looking at the radical functions. So when we take the derivatives of these radical functions and using the same formula, right? So h prime of x, that is equal to limit as h approaches to 0 of f of x plus h minus f of x all over h. Substituting this into the functions, and we got this. Now what we're going to do is we're going to try to rationalize the numerator by multiplying the conjugate factors of the numerator. Okay, let's try to do that. So multiplying with the conjugate factor on the numerator, that will become difference of 2 squared. So square and square root cancels out. I will have 1 minus x minus h minus 1 minus x. And in the denominator, h times this conjugate factor. Simplifying further on the numerator, when you distribute the negative, then 1 and negative 1 will become 0. Negative x and positive x becomes 0. So I have negative h over h times square root of 1 minus x minus h plus square root of 1 minus x. Now, what I can do is I can, reduce the h together, and then that will give us limit as h approaches to 0 of negative 1 over square root of x minus h minus 1 plus square root of 1 minus x. Oh, my bad, sorry. I have different order. 1 minus h. Now direct substitution is applicable, so when I apply the direct substitutions, this will give us square root of 1 minus 0 minus x plus square root of 1 minus x. I have two of them, so this will become minus 1 over negative 1 over 2 square root of 1 minus x. That will be my final answer, which is the h prime of x, right? Derivative of h. Now, next example is a polynomial, which should be much easier, but a lot more work because of the cube right there. Okay? So, finding out the derivative of the functions, we use the same formula and then substitute x plus h. Let's try to do that. So, g prime of x, right? Limit as h approaches 0, f of x plus h minus f of x. So I substitute x plus h into the functions, and this should have been not f, this should have been g, right? Make sure you write it properly along with that. And that means, like, you know, I made a mistake on a previous example also. Right here, instead of saying f of x, I should say the what h of x plus that and h, right? So this is like a bad notations, right, for this one, because, like, you know, h is everywhere, so you might get confused. So be careful with that. So this is a very bad notations for, right? I use a function. See, h, f, g, h, those are just the name of the functions, but you make sure you don't mix up with this h right here. What are we talking about, right? H is the distance. So when we cube x plus h, right, from what we learned in previously, you can FOIL it one by one, or you can use binomial theorem to find out the coefficients, or you can use the Pascal triangle, right, to get the coefficient, because this one will be cubed. So that's where we got 1, 3, 3, 1. So now I have quickly, like, you know, computing this, that give us x to the third plus 3x squared h plus 3xh squared plus h to the third, and then minus, and I'm going to distribute it whatever I folded right here, which is going to be 2x squared minus, double it up, so anyway, minus 4xh, and then minus 2h squared. And then lastly, it will be plus x plus h, distributing the negative into the second grouping symbol. And we got this. So now, continue on simplifying this. Limit as h approaches to 0. X to the third power. X to the third power. It's gone, right? So let me use a different color so that we can get this better. So x to the third power is gone. X to the second power. X to the second power is gone. And then x and x, is there any x in here? Yep, x and x is gone. So notice that all the terms that left over is with h, so I can substitute, I can factor out right away, right, to make it easier for me to continue this. So factor out h, that will give me 3x squared plus 3xh plus h to the second power minus 4x, and then minus 2h plus 1 all over h, and which give us limit as h approaches to 0 of 3x squared. Now I'm going to try to combine everything that I can, or maybe not, right? Plus 3xh plus h squared minus 4x minus 2h plus 1. And then when I substitute 0 for this, right, all the h, and this term, I have nothing to substitute, that will be x squared, and plus 3x times 0 plus 0 squared plus minus 4x, right? minus 4x minus 2 times 0 plus 1. So therefore, my final answer in this case, g prime of x, that is equal to 3x squared minus 4x plus 1. And that would be the derivative of this functions. Now later on, it will be, in the next sessions, we're going to be learning how to use the formula to take the derivative, which will be much, much easier and faster, right? This is by definition. That's why it takes a long process to do with it. Now, what we want to do is we want to sketch both of the graph on here, okay? Both of the graph on here. So we know that the g function, let's take a look at this. G of x is equal to x to the third power, okay? X to the third power minus 2x squared plus x. X to the third power minus 2x squared plus x. So what I can do is I can factor x out. That will give me x squared minus 2x plus 1, which is x and then x minus 1 quantity square. So we have, from here, we know how to graph the polynomials from the pre-calc. This is third power. So that tells me the end behavior is going like this. And in between, we're going to have 3 zeros, right? So we're going to have 3 zeros right here in between. And we know that one of the zeros, right? When g of x is equal to 0, that's one of the 0 is what x is equal to 0. And the other one is what x equal to 1 from here, right? From x minus 1 factor. And I have 2 of them, so this is multiplicity of 2. And what is the multiplicity of 2? If multiplicity is odd, then the graph will pass through that 0. If the multiplicity is even, the graph will touch it at that point. So let's try to graph that. But we just don't know how tall and how high and how low between this is going to be, right? I'm just going to be sketching it. So at 0, x is 0, it will be 0 right here. And then we know the end behavior and multiplicity at 1 is multiplicity at 1 and the multiplicity of 2. So the graph will touch and go back off. So my graph is going to look like this, going down, and then shoot up somewhere and then peak and then come back down and then go like this. Okay. And again, I don't exactly know what is happening in between 0 and 1 at this point, right? Later on, we will be able to use in chapter 3, we will be able to use, finding the local maximum, local minimum, right? Using the first derivative test to find out where is the peak is going to be exactly, and how this graph is going to be concave up or concave down. But right now, it's just a sketch with what we learned, previously, and then what we got right now. Now, using this, I can find out what is my G prime graph going to be. So this is the graph G. And G prime graph, you can use, okay, you can always use this quadratic to graph it, find out the vertex and everything, right? Or like you can sketch it. And if we find out the vertex and everything, that will be neater because we will exactly know what's going to happen in between and stuff. Right? But we can always start with this. So g prime of x, that is equal to what? 3x to the second minus 4x minus 1. So I can factor it out. I can clearly see that the graph of the g prime, which is the first derivative, is going to be a parabola. And this is going to give us, is that minus 4 or plus 1? It's a plus. Yeah, I copied it down wrong. So it's plus. So this will be -1 and then x minus 1. So you can see that when g prime is equal to 0, that means what? My x is going to be at 1/3 and x is equal to 1. Right? Those two are zeros. And we already know that already from, what we learned earlier, because right here, we're going to have what? A horizontal tangent line. So for sure, my G prime graph right here will be 0. And I pointing out that where is the peak, we don't know. From here, we found out it's 1/3. So approximately, I'm, right there. If I, break it into 3 units, 3 equal units, 1/3 is around there, right? So, which is, close, very close to it. So now what I can do is I can graph, right here is a 0, and right here is another 0 for the functions. And you see that the slopes are always increasing. Right? The slope are always increasing. Let me use a different color so that you can see better. Right here and right here is a 0 because of horizontal tangent line. And slopes are always increasing and it decreasing between these two, right? And then increasing again. So when the slope is decreasing, that means what? It will go below the x-axis. And when slopes are increasing, it will be what? Go back to what? So we got a parabola as we predicted right here. So this is my what? G prime graph. So a little bit messier because mine scale it a little bit small. I should scale it every 3 units and then you should see better. But hopefully you get an idea, right? From here. Now, continuing moving away from here, right? Then what we want to do is we want to ask these questions because we learn continuity in chapter 8, 1.8. Now, if the function, the questions will be, if the function is continuous, that's a differentiable, right? And what we can do is we can look at this and then, give you a quick examples of it. So if I have a function's absolute value of x, and we want to find the derivatives at 0. So that means limit as x approaches to 0 of this absolute value functions, which we need to talk about the left-hand limit and right-hand limits. And as you can see, the left-hand limit and right-hand limit are different, so the limit does not exist. That basically means it's not differentiable at 0. Okay, so it's not differentiable at 0. So what that tells us is, when you look at the picture of, the graph right here, right? When you look at the graph, this is absolute value of x. It is continuous, but however, it is not differentiable at what? 0, 0 original, right? Because the limit, left-hand side limit and right-hand side limits are different on the formula, derivative formula. And also, as you can look at it, the other one, g of x is square root of x. And does it g prime of x continue? 0 exists. And when I computed g prime of 0, limit as h approaches to 0 from positive side, because we know that this is one-sided limit. So you can see that the limits go to infinity. So once again, in here, we can talk about continuous from the right, but however, it's still not differentiable at 0, 0. So therefore, it's continuous differentiable, and the answer will be what? No, in this case. Okay, the answer is no. So the function is continuous doesn't mean that it is differentiable at everywhere, right? Within that continuity. So, but however, the other way around is true. If f is differentiable at a, then f is continuous at a. That is true, right? The other way around is true, because if it is a differentiable, meaning the limit exists, then for sure, a function will be continuous as functions define. So another thing that we want to look at and then start introducing is, can we differentiate these operations over and over again, right? So this is what we want to talk about, higher derivatives, and it has meaning to it also. So when we talk about the first derivative, that we will use f prime, that is dy over dx. That's the first derivative. And then when we talk about derivative of this f prime, then we are talking about the second derivative, which is f double prime. And we will write it down as d to the second y over dx squared. Right? And continuing, if you take derivative of the second derivative functions, then we will get the third derivative, which is f triple prime, and then d to the third power right here, Okay, third power, that's a typo. Make sure you change that. Y and then all over dx to the third power also. Now, anything after the third derivative, we don't write down prime anymore. We will write it down as what? The numbers. If you have n derivatives, right, then f prime of n, right, we write it down as f n, right? So if it is like fourth derivative, it will be f fourth of the functions. And then this will be d fourth y over dx to the fourth, like that, right? So on and so forth, and then you continue on from there on. So finally, if f the derivative of f to the n fn derivatives, then we need to add one more. So it will be dn plus 1, right? Fn plus 1, this one should be, right? The n derivatives. And derivatives of n plus, n derivatives. Okay, yeah, n derivatives, that will be n. So dn plus 1, and then dn plus y to the dn. Okay. So this is if we continue on the higher derivative, this is what's going to happen, right? And this is the notation, but one quick example that I want to give to you, the point is right here. We talk about the position functions, s of t, right? And that's the position functions. If we take the first derivative, which is instantaneous rate of change of the positions, right? Which is, that will become what we named the velocity, right? The instantaneous rate of change, which is a velocity. So the velocity function is equivalent to what? The first derivative of the position function. Now, if you take the velocity, derivative of the velocity, then that will become the acceleration function, because instantaneous rate of change of the velocity, right? So that will become accelerations. And that will be what? The first derivative of the velocity functions. But however, it will be the second derivative of what? The position function. So therefore, the higher derivative has a meaning to in a certain application problem. And there is a third derivative of position functions. It has a term to it. You can find that out in your textbook, right? And the idea of this section is very similar to what we talked about, last time. This is a little bit more like, generalizing. Instead of taking derivative at a point, we will talk about taking derivative as a function in general everywhere in the functions. If it is the limit, if this limit exists. Yeah? And as I pointed out, this formula will use less now because what we don't want to talk about f prime of x to be f of x minus f of x. Right? And here's the homework, and then you can try to practice it, and then don't hesitate to ask me a question if you have any.